Look, let's just get right into it, because honestly, when you really take a step back and look at it, the entire history of computer science isn't some noble, shiny pursuit of universal truth. Not even close. It's actually a frantic, exhausted, stress-induced scramble to outsource human brain power. We're tired. Our brains are incredibly messy, and for literally millennia, we've been desperately trying to build anything, just anything, that can hold on to information so we don't have to. So welcome to this explainer, where we're going to trace the deeply human, and frankly deeply absurd, arc of our endless itch to outsource our own minds.
So the obvious question here is, why? Why have we spent 4 millennia desperately trying to build external hard drives for our brains? Well, it's pretty simple. Human memory is an absolute nightmare. Imagine you're living in an ancient society, and you need to keep track of who owes who grain, who owes livestock, or who is just drowning in debt. Trying to hold all those complex, vital social ledgers in your head alone, yeah, that's a recipe for disaster. We needed a hardware fix.
And that very first hardware fix happened around 4000 BCE in ancient Sumer. Picture it. Someone sat down completely fed up with trying to remember endless grain debts and just picked up a wooden frame strung with beads. This wasn't some little toy. The abacus was the absolute first piece of hardware designed to fix our flawed, forgetful meat brains.
The contrast here is just striking. On one side, you've got the messy, abstract, incredibly fragile nature of numbers floating around in a human head, and on the other, the concrete abacus. It did something profound, really. It turned abstract thought into something physical. You can move a bead, look at it, and trust it completely. Honestly, that satisfying, reliable click of wood on wood, that is the exact same itch that drives every modern silicon chip sitting on your desk today.
Section 1. Rage, Gears, and Symbols. Fast forward to the 1800s, where the sheer annoyance of human error finally pushed one British mathematician right over the edge. Meet Charles Babbage. A biographer literally called this guy an irascible genius. And why was he so perpetually angry? Because back then, computer was an actual job title. Rooms full of actual humans did math by hand to create navigation and artillery tables. And guess what? Humans get bored. They write down the wrong digit, a ship crashes into a reef, or an artillery shell lands 200 meters off target. Babbage looked at these error-riddled tables with pure, unadulterated rage and decided right then and there he was going to build a machine to permanently replace the human element.
His blueprint for the analytical engine in the 1830s was just absurdly ambitious. He envisioned a store that could hold 1,000 50-digit numbers. That's basically RAM. He designed a mill to process them, which is your CPU, and it would take inputs via punched cards, an idea he shamelessly borrowed from automated weaving looms. Babbage was out there designing a general-purpose, programmable, mechanical computer a full century before the technology even existed to actually build the thing.
But here's where it gets really fascinating. Babbage had a collaborator, Ada Lovelace, who looked at his gears and made this brilliant conceptual leap. She grasped the concept of symbol manipulation. She realized that if you can express anything as a set of logical rules, whether that's letters, musical notes, or patterns, the machine could process it. It wasn't just a big calculator anymore. It was the birth of universal logic.
Section 2. Dimming the neighborhood. We jump to the World War II era. Victorian gears just weren't precise enough anymore, so the urgent need to calculate artillery trajectories escalated our outsourcing attempts from brass to raw electricity.
Just look at that power draw, 150 kilowatts. That is the sheer, absurd amount of electricity required by ENIAC, the electronic behemoth the U.S. Army built back in 1945. It weighed 30 tons, it took up an entire room, and I absolutely love this historical detail. When they fired this thing up to crunch differential equations, it drew so much juice that it literally dimmed the lights in the surrounding neighborhood. But of course, that speed came with an agonizing trade-off. Yes, ENIAC gave us a blistering 5,000 additions per second, which was 1,000 times faster than the mechanical machines. But to get that speed, it relied on 18,000 incredibly fragile glass vacuum tubes that burned dangerously hot. A tube failed every 2 days. You essentially had someone constantly crawling through the guts of this massive machine with a flashlight, desperately hunting for burned-out glass. It was faster, for sure, but it was incredibly fragile.
Section 3. The fragile security illusion. Thankfully, we eventually figured out how to shrink those hot vacuum tubes into tiny, reliable, microscopic transistors on silicon chips. But once the hardware became rock solid, the existential dread just shifted. It moved from worrying about burned-out tubes to sweating over complex mathematics.
Consider the P versus NP problem. It's literally the most famous unsolved problem in computer science. P problems are easy. The time it takes to solve them scales pretty reasonably. But NP problems, the solving time is explosive. Think about finding the absolute shortest route through hundreds of cities. A computer might take longer than the age of the universe to solve it from scratch. But, and here is the massive twist, if someone just hands you the answer, verifying it takes mere seconds. It is practically impossible to solve, but trivially easy to check.
Which brings us to this literal million-dollar question. Is the wall between P and NP real, or is it just an illusion? Like, are NP problems actually hard, or are we just currently too stupid to know the mathematical trick to solving them quickly?
And why does this matter to you? Because our entire modern digital life depends on that wall being real. Modern encryption, like the RSA algorithm currently guarding your web browser, works entirely on the unproven hunch that NP problems are actually hard. We lock up your bank accounts, your private messages, and the entire global financial infrastructure based on the assumption that it's easy to multiply two massive prime numbers together, but impossibly hard to reverse engineer them. If someone proves that wall is an illusion, the entire internet security evaporates overnight.
Section 4. Confident, coherent, and wrong. So while the theoreticians sweat over the math, the engineers just kept building. And eventually, we got so incredibly tired of writing line after line of explicit software code that we decided to just let massive networks guess the patterns for us.
Which brings us to the terrifying reality of the modern AI black box. These models have hundreds of billions of parameters now. They are operating at a massive, completely uninterpretable scale. They rely on opaque, implicit logic that even their own creators don't fully understand. And worse, they can be subtly steered by adversarial inputs that are entirely invisible to the human eye. We are currently facing a massive verification gap where we're deploying these unreadable systems into insanely high-stakes environments like medicine and autonomous driving.
So, welcome to the era of corporate AI slop. These massive pattern matchers will give you confident, coherent, and completely wrong outputs because they aren't reasoning the way you or I do. They are just statistically hallucinating the next most likely word in a sequence. It's a miracle of engineering, absolutely, but it is fundamentally disconnected from the truth.
Section 5. The quantum reset. If AI is bending reality, our final escalation threatens to break it entirely. This is the point where the actual fundamental laws of physics threaten to destroy all the math we just spent decades building.
Okay, let's look at qubit mechanics real quick. In classical computing, a bit is a 0 or a 1. It's a light switch. But a quantum bit, or qubit, throws that completely out the window. Step 1, superposition. It can explore 0 and 1 paths simultaneously. Step 2, entanglement. Qubits become instantaneously correlated across distance in ways that make absolute zero classical sense. And step 3, interference. The quantum computer can literally amplify the paths leading to the correct answer and cancel out the wrong ones. It is bypassing classical binary limits entirely.
And here is the existential threat. Back in 1994, Peter Shor figured out that if you can build a stable quantum computer, you can run what's known as Shor's algorithm. Remember that RSA encryption we talked about? The one guarding your bank that would take billions of years for a regular computer to crack? Yeah, Shor's algorithm turns our most advanced cryptographic defenses into absolute dust. It solves that impossible math in a matter of hours. And guys, this isn't science fiction for the year 2100. It is a frantic, real-time scramble happening right now. Just look at this timeline. In 2024, the US already began standardizing post-quantum cryptography. Tech giants expect to reach quantum advantage by 2026. And by the late 2020s, we might actually see fully fault-tolerant quantum computing. We are quite literally in a race against the clock to rip out and replace the entire planet's global digital infrastructure before quantum computers get stable enough to break it all.
Which leaves us with this final, lingering thought. We started 4,000 years ago sliding wooden beads on a frame because our brains just couldn't remember who owed who a bushel of wheat. And now, we built machines so profoundly complex and scaled them up so massively that they hallucinate reality and threaten to crack the mathematical foundations of global privacy. So what happens when the ultimate machine we built to fix our memory ends up erasing our security entirely? That's the question we're all going to have to answer very soon. Thanks for diving into this explainer with me, and I'll catch you on the next one.